Yeah, give me the background. When I go first, you almost go into the presentation and also more about what those are. So, just to give a little overview. The first part of the presentation is going to be a little bit background from what procedural generation is and what mechanisms are. Then we're going to talk a little bit about the high level of how we construct each component. Then we'll talk about the helper classes that we use to make that construction happen. We'll show some example code and some results. And I'll talk about where to go with here and if any questions that we have. Okay, so procedural generation. In short, it's generating any kind of content sort of dynamically. And so there's a couple ways this can be done. You can generate something once and then save it as a model and use it, or generate something based on a seed, store that seed to get the same random numbers each time, or you can generate on the fly as a totally different and you can generate anything, textures, AI stuff, dialogue, your maps, really anything you can think of. And of course, for this presentation, we'll be generating matches. So the four key components of the match are the vertices, the triangles, the UVs, and the normals. And we're going to talk about those on the next slide. And here I took a picture of being probably a lot of these heard of called No Man's Sky. It was kind of a big deal for procedural generation because the game had 15 billion planets and it was very exciting. But it also started with a couple of the cons of procedural generation. So I'm going to focus on the pros here, but if you have any questions or you want to discuss the drawbacks of procedural stuff afterwards, please ask the question. I'd love to talk about it. So the components of procedural matches, as we mentioned, the first is the vertices. That's just an array of 1, 2, 3 states. And in Unity, the vertices of match are stored as a vector view of fields. So the 3 components x, y, and 2 positions. And then the 3 other mesh components kind of fit off of that. So we have the triangles array, which is an array against that corresponds to the vertices. So when you think of match and you have triangles, it's like the lines that connect your vertices, right? And so each triangle in Unity is just 3 indices that correspond to the vertex indices in the grid array. And this is where order starts to matter because depending on the lining order you get into later, your first index order actually determines which direction your triangle is facing in. And so with the vertices meshes, that kind of gives you like the solid part of your mesh. But there's 2 more components to actually see. And the first is the normals, which is again an array of vector views and it corresponds to the vertices. And the point of normals is how light responds to your vertices. And that's interpolated over the course of the triangles that I connected to. So correct normals will do good lighting, and incorrect normals will make your map go black. And finally, we have the UVs, or UVW, and that's an array of vector views, x, y components. And this actually maps whether texture you're using to the coordinates that you specify in your vector view. And it's a range from 0 to 1. And again, like the normals, will interpolate over the course of the triangle. So if you have, say, a polygon and bottom corner is 0, 0, and the top right is 1, 1, over the course of that polygon, your UVs will cause the texture to map linearly onto the polygon. But UVs are really tricky, and we're going to talk about those. So, first things first is vertices. The good thing about generating the vertices, and this is what you should do first, is that order doesn't matter yet, because you can pretty much generate them any way you want, depending on your model topology or depending on what methods are easiest for that model. So a couple examples that I use are to generate around a center point. Say you want an end-state-sided polygon that creates a circular shape, you can generate verts around the polygon, or you can extend out from one edge. With a method example of the box. And oftentimes the vertices usually do fixed, and we'll talk a little more about that later. But so if you think of a normal cube, you'd probably say that has 8 vertices, but in Unity, in pretty much any modeling environment, a cube actually has 24 vertices. And that's because for every non-smooth condition between edges, you're going to have 2 vertices. We'll talk about this. And for every corner, you'll need 3. And if you have a vertex that's touching 4 bases, But so this code in the bottom right corner is a little bit of a I don't know how visible that is, but that is one way that you can generate verts from one position and then extents and a width. It'll just give you a quad and you can pass that along. And triangles. So triangles are actually the most straightforward, and say you can actually vertices together. The most important thing about generating triangles is to remember the winding order. So for Unity, we have a clockwise winding order. That means that you just want to put your vertices in clockwise order in order to get the triangles to have an outward facing mesh. And so if you don't, if you're just say use counterclockwise vert order, they would actually face in, which sometimes you want. Sometimes it's easier for you to generate a little bit one orientation than flip them to face in. That's very common for use in modeling, but for procedural generation, it's easier to not deal with them. And optionally, you have to have the drivers for each vert. So say later on in your generation algorithm, if you want to know what triangles the vertex is attached to, maybe your procedure depends on what happens to the previous triangles, then you can do that. And so I highly recommend exploring those somewhere. And actually, dedicated class for that. We'll talk a little bit about that. So here our example is the geosphere. It is a sphere that's composed of triangles. Normal spheres tend to get a lot of polygons that kind of all come together at the top. This is an easy way to represent a sphere as quads. So geospheres, you can reconcile that. The triangles with that are highlighted in white. So next is generating normals. Again, this is pretty straightforward. To get a single normal, you need to take a cross product of two edges of a triangle. And again, the order matters because normals define lighting. And if your normal is backwards, you'll have a mesh that reacts to lights as though the light is shaped the other side. And given that your polygons are single-sided, your full mesh doesn't work. So follow the winding order. You use the clockwise winding order in most algorithms do that. And so normally, if you just like make a model and you don't assign any normals, you'll get this really blocky look. Because the lights for each quad are just dependent on the normal for the vertex of that quad. But instead, you want a smooth like shape most of the time. And that's referred to as normal smoothing or additive. And so if you look at that. So if you think of a box and you give it normals that have not been averaged yet, you can notice they just kind of point out in the direction of each base. Because each polygon has a distinct 90-degree angle between them. And then if you unify those normals using the averaging process, then the normals point out in the average of the three polygons in each vertex touching. And the result is they point out, and you can see you get a really smooth looking shape here. Now, for a box, you probably would want it to look rough, so you would not average normals, but you usually have some kind of smoothing constant that defines how sharp a curve should be before we grade them on. So that's really easy. You just take the average of all the normals the way you would take any average, just add it on and divide by 1. And that's about it for normals. Then finally, the UVs, and I think this is the most difficult part by far, because there's really no one right way to generate UVs. It's actually a big part of the modeling process is trying to figure out how you want your texture to map, how many textures you have. You can say repeat a texture over the course of the mesh, think like a really long plane. If you want a grass texture on your plane, you probably don't want the one texture to stretch all the way across one repeated. In stretch, you can map to a shape, so very often you map to like a sphere or map to a cylinder. And then for a more complex mesh, forget about this. It's very hard to do unwrap for UVs. So it's generating UVs is very tricky, and you're going to need a lot of different solutions depending on the mesh that you're creating. For procedural work, I think you can get away a lot with just doing like competing over a set unit size if you keep your unit size constant. And there's a couple examples of repeating and stretching after there, but it's pretty complicated stuff, and I have far from the next. Okay, and finally, we'll just go over this. Finalizing a mesh, this is something we do every time they procedurally create something, so you can just abstract it to a method. You create your mesh filter, your mesh renderer. If you want to use all your average normals, you set all the components. And it's pretty expensive, but if you want to have accurate collision and downspec, then you calculate your downs and your collector your mesh. And say you create like a high poly mesh, then you also need a low poly mesh for the collider. And you can set here, and you set your material. And so, yeah, that's pretty much anytime you can procedurally generate information. And so there's a few key helper classes that we need to make this happen, because that's kind of a high-level overview. There's a lot of code that goes into it. And so just to touch on a couple of those, the first is the vertex dictionary. And I don't think I mentioned this earlier, but you're going to log through your vertices to dictionary position and orientation to the vertex, because very often, if you have, say, that key we talked about before, we have 3 vertices for each one. If you have just a dictionary, of course, you can have your keys. So if you just use the position as your key, that's not going to work. So the full solution to this is use the embedded dictionary, which is positioned to the second of orientation to the vector itself. And in the vertex dict, I found that it was also useful to store a bunch of data about, like, I mentioned earlier, kind of tribes, other nearby words, things that, you know, and because you can use the index of vertex to reference the indices of all the normals, the waves, the birds, and the tribes. Because you can use the indices for that, you don't have to worry about copying data. It's a good idea to kind of keep track of all this in the next class. And then we kind of get from the generation, which is the generate match class. And the core method that generate match handles is to propagate quad and generate quad. And so with generate quad, this is where we create triangles. You'll see most of the time it's easier to generate quads, which is just 2 triangles that create a square. But sometimes, like in the case of geosphere, you need tribes, so you can make the core vertex optional. But this is where you're kind of want to actually call all that generation stuff that we laid out before is generate quad. And if you want to extend a quad out from the corner, you have to go for that earlier. So you have the corner and you want a square out of that based on an extended. That's what we call propagate quad. And I think these are 2 good high-level functions to start with. You can add a lot more later depending on how you're finding yourself generating stuff. And the generate match class is also responsible for introducing the vertex dictionary, and it does some nothing too crazy. Rotating plots, rotating vectors, between plots, calculating elements, all that stuff. Quaternion is just a 4x4 matrix that you can use to store rotations. They're pretty cool. And so another helper class that I would recommend creating is the match shapes class, which will integrate with generating match to construct some very basic shapes. So in my match shapes class so far, I put in 1 for cylinders, 1 for spheres, 1 for caps, and then some of the basic ones for planes. All that stuff here. I think I put a spiral in there. And so, for instance, if you take a generated cylinder, that will input an extent and a circumference and a number of sides, and it'll just build for you an inside of the cylinder while interfacing with the match generator class to actually create that match. And that's useful for things like creating these boxes and objects that use enough pieces, they start to curve. So, right? And we'll see more of that. And finally, the mesh effects class, I recommend taking this sort of separate from the mesh shapes class, and this is for effects like if you want to map your mesh to, say, a sine curve or some kind of transformation or further noise, something like that, then you want to use it's basically like animating your mesh, but you can do it in real time because you have access to all the vertices and all the mesh data. And so one that I played around with a lot of fun is just mapping it to a sine curve and modifying the speed and amplitude and number of waves. And you can use an effect once to create a static effect, like you can turn a sphere into a flower by mapping it to a sine curve, but the topology goes around it. It's really cool. Or you can just have a wave or any of the other effects happening in your drop table, and you'll get like an animated mesh, like wobble or anything. And those are our four helper classes. And now we're going to look at a few examples. The first is the most basic and then is spiral. So what we do with the spiral is very simple. You can see the code here. We start at the bottom right corner, and this is where they use that propagate quad method, which again takes in 1 vertex and then extends and a width, and just calculate the other 3 vertices, turns them into a quad, and then returns the next bottom right vertex. So you can keep redefining your current position, and then if you decrease the extent as you go down, you do that for loop going down the way of the spiral where it starts to change the This is very cool, very basic, but this is the result of that, with all of our components and some proper courtesies and try to be able to see it. Then we get into some more complex stuff. We have cylinders, and you can do a lot with the cylinders. Use the seams actually make a lot of cool shapes. And so the key difference between the spiral and cylinders is kind of we do not decrease the extent, and instead we'll actually take it as circumference. We take it as circumference, and it just goes around and there's basically a file that doesn't decrease the extent. But it also keeps track of your front and back vertices, because very often, say you're getting oil drum for a game, very commonly with asset, you'll want to top and bottom go in another case. Otherwise, you have open cylinders. Say like happen, and the two cases you make are based on edge curve or center curve. And I don't want to go into too much detail because this one's going to talk about it, but long story short, you want to use the center half because if you start deforming your cylinder and you're using edge half, then you're going to see times where they don't make sense. They kind of go with the issue. And you notice on this next slide coming up that the UV-W mapping did not work great. And the reason is the UV mapping, the procedure that I mentioned before, were all hard-coded for a quad at that time. So it was attempting to, the quads that are going around cylinders look pretty good, but then the tries that are usually very fast, we can't really have out of quads. They don't have four effects, so they just kind of work there. So you can do that in any line at. And so this is actually just using cylinders and spheres. The top left is a sphere, and the top right is a sphere that has been blown up based on that sine curve once. So like I mentioned, you get a sphere and flower. Creating a lot of that. Then we start getting into like mass producing stuff. So I tried to put flowers into a scene. Flowers. So we have two components to the flower scene, which is an end-sided cylinder for the stem. And just we aim your flowers and very hard to see how long you have like your water side and then we have one side of the scene for generating the petals, which is it curves around based on the sort of center axis. And it also curves in at the same time, and it fills out the polygons that way, so you get the benefit effect. And right now, it's using a debug actually, but I will see later if we were to apply, say, a transparent L vector with each edge cut out, so you get a smooth curve, then you can make a really cool looking thing that does look like a flower. All my parents said it was really nice. And the key thing here is also centering. There are different ways to get rid of the talk about. This time I utilize centering for the stem and center tapping for the petals, because otherwise they would be very hard to place factory due to the fact they have very properties. So there's a bunch of flower type things on the screen. They all have custom stem sizes, stem widths, number of petals, petal width, petal curve, number of curve segments. Every component has been randomized. And it was pretty cool. And now a very simple example was to make a brick wall. This is a pretty common thing that you actually do on map or a model map for. I thought we wanted to actually create the polygon for that. And so this is a much more simple example. It's pretty easy to replicate this. You create a single thin box for like the mortar or the building. Actually, for brick walls. And then you create an array of cubes, and you can shift them forward in the procedural process. And very, very simple, and you get this nice texture. Sort of each brick in the walls is pushed out, or pushed in a little bit. This one nice thing about procedural work is normally if you're doing this in an object program, an artist would have to say create an array and then manually move them or move them based on some kind of notice. If you just do that in coding in 15 minutes. This is a classic pipe screensaver where a bunch of pipes can fly around the screen and move it out. And I love this one. It's pretty cool. So I decided to make that in my procedural mention. I guess. And so the key thing for the pipes is we can combine uncapped cylinders, which means that they will be created inside and outside faces, and they won't be blocked off on the ends. And randomize the length and the color. And then after each pipe, we can either rotate them or shift them depending on the random axis. And if the axis is not a rotation, then we create an elbow joint between the segments. a little bit tricky. I'll show you the screenshot.
Oh, this is so
If it was a little brighter, you can see here we have a bunch of cylindrical pipes, and each corner is being connected with an elbow joint, as I mentioned before. And the way I was able to achieve this, not to do too much backbreaking work, is I stored the front verts from the front half of the previous cylinder and the verts from the back half of the next cylinder. Even though they don't have a cap face, I still have the cap verts. And then I just stitch them together one by one onto the generic mesh polygons. And the result is very nice, very nice. So where can you go from here? This is, there's a lot of setup, admittedly, as you can see, getting some procedural innovation. Unity wasn't really designed for it, but it has the tools to do it. So this is a lot of experiment that I want to do. One thing I'm really interested in is handle process. You can map a procedural mesh to a fractal based on, say, you put in like the number of iterations and they calculate the position for each vertex in your use case. Basically, really awesome designs. I highly recommend checking out the process. And then there's the idea of making more complex objects through mesh manipulation. So a traditional modeling environment has things like extrude, stretch, squeeze, bend, or and all of these are really useful for humans, but they can also be great for procedural code as well. Say you wanted a hemisphere that was squished down, a pancake shape, I don't know, but you use manipulation like that. And then one thing I want is some Boolean operations. So you could say or subtract or divide one mesh from another. You can make procedural factors, procedural materials, or compound objects. Or you can do like procedural shader code. So the key difference between mesh and a shader is the shader does things on purpose level, whereas the mesh will do things on the vertex level. So if you want like a really high polygon model, but you can't avoid any polygons in your workflow, then you can do a shader generation where you specify a function of each pixel instead, and so it calculates one vector for each one, x, y, z coordinate for each pixel instead, and you're not going to get about any number of polygons because you algorithm. And that's it. And always, if you do